Good morning, and thank you all for coming today. We have a rather thin in-person crowd, but there are a number of people online, so it looks better than it may appear at first glance. I'm Mike McFadden, and on behalf of my co-conveners of this session, I'd like to welcome you to this union session on transformative discoveries, technological breakthroughs, and societal challenges, lessons from the past as guideposts to the future. This is one of two union sessions that is being convened by the AGU College of Fellows Legacy Committee, which is chaired by Eileen Hoffman, who is helping with co-chairing this meeting this morning. The second is on Friday on imaging the Earth's surface. The mission of AGU's Legacy Committee is to promote appreciation of how Earth and space science has advanced our understanding of natural systems and how that understanding has benefited us as a society. And so this morning we'll hear from three distinguished speakers on topics of great scientific interest and societal consequence. The speakers will have 25 minutes for their presentations. You'll see an orange light go on at 22 minutes, and then the red light will go on at 25 minutes, for which time you should wrap up. And then we'll have questions afterwards. So our first speaker this morning is Professor Dan Baker from the University of Colorado, who, among other accolades, has received AGU's highest honor, the William Bowie Medal, in 2018. And Dan will speak to us on Earth's Van Allen radiation belts. Dan?
Much, Mike, and someone can pull up my slides. I'll get started. Thank you to the conveners for organizing this. Thanks for the fellows doing this. It's very, very important to have more interdisciplinary work. Great. So can we go to full screen on that one? I guess it is there. Okay. And do I advance it with this one? On the 4th of October of 1957, to the shock and surprise of much of the world, the then Soviet Union launched into space the first artificial satellite of the Earth. They called it Sputnik, which means companion, and it was little more than a radio beacon, but it was alarming to the world, realizing that the missiles from the Soviet Union could put something into space and in principle could put a nuclear payload anywhere on the surface of the Earth. This was shocking and led to quite a large amount of concern around the world. Less than a month later, a much more sophisticated spacecraft was put into orbit. This was Sputnik 2. This had on board the dog Laika, and also had a sophisticated package to measure cosmic rays and radiation in space. This was developed by Sergei Vernov from Moscow State University. The apogee of Sputnik 2 was over Australia, not over Soviet territory. The data were encoded, and so the Australians recorded the data and asked for the code to interpret the data. The Soviets refused. The Soviets demanded the data, and the Australians refused. And so the Vernov belts faded into oblivion, and it fell to these three men to make the first great discovery of the space age. Here on our left is William Pickering, who was the director of the Jet Propulsion Laboratory in Pasadena at the time. On the right is Wernher von Braun, the rocketeer who developed the rocket to get in space. In the middle is James Van Allen, who developed the instrumentation for the Explorer 1, the replica, which is held aloft. What they discovered was the Earth is shrouded in belts of very high energy particles radiation. This led to Van Allen appearing not once but twice on the cover of Time magazine, and it initiated, I would say, really observational space physics. What did they discover? Well, they really discovered that the Earth has two belts or toroids of radiation around them. The inner belt is comprised primarily of very high energy ions, mostly protons. The outer belt is comprised of a much more variable flux of very high energy electrons. It's probable that the U.S. instruments first detected the inner zone, the inner belt, and the outer belt from the higher latitude. Soviet spacecraft was probably detecting the outer belt. Eventually, the Soviets did interpret their data properly. Over time, we've learned a lot more about, of course, about the Earth environment. We have known for a very long time that the Earth has an intrinsic magnetic field, of course. The core part of this is rather dipolar in character. As one goes out further, the system becomes much more variable. The entire region called the magnetosphere is confined by the flow of solar wind on the sunward side, extended into a long comet-like tail. The solar wind interacts with the magnetosphere, forms a bow shock. There's a magnetopause layer that's often portrayed in textbooks as rather smooth and very stable, but it's really undulating and changing on essentially all time scales. As one looks more deeply into the system, there are several different kinds of energetic and cold plasma populations. The cold plasma population is called the plasmasphere. It supports a wide variety of waves. There's an extraterrestrial ring current made up of energetic ions, and then the Van Allen radiation belts are commingled with that. This whole system is driven by the flow of the solar wind, continuous flow from the sun. Under the right circumstances, this can load energy into the reservoir of energy on the night side called the plasma sheet. And when the interplanetary magnetic field is opposed to the Earth's magnetic field, then there can be very substantial energy transfer from the solar wind into the magnetosphere. This sort of opens the gate to allow energy to flow into the system very effectively. And this leads to what are commonly called geomagnetic storms. And these storms can produce very large energy inputs into the Earth system, can pump up the inner populations that I talked about, and can lead to very powerful storms on the Earth's surface, and can lead to great enhancements of the aurora. And of course, these can be seen from space and have also intrigued humans as seen from below for a very long time. And so the understanding of how all of these complex systems interact with one another is one of the real challenges that we're studying. Now, why are we concerned about this? Well, the environment around the Earth has become over time populated with much more of spacecraft, and of course the Earth itself has technological systems. So it's a virtual cocoon that surrounds the Earth. Right now, there are thousands of spacecraft in low Earth orbit. There was just announced a couple of weeks ago that SpaceX has been approved to put another 7,500 spacecraft into low Earth orbit. And if we back off and look at the even bigger picture, there are over 6,000 active spacecraft, not to mention all the inactive spacecraft that are out there. And it's estimated that by 2030, there could be tens of thousands of spacecraft in Earth orbit. And all of these spacecraft are subject to the space environment, to the radiation belts that I talked about. And these effects can be surface charging from relatively low energy particles. But the high energy particles, the inner zone protons and the outer zone electrons, can cause failure of satellites. This is one of the features we call space weather. So it was decided that after almost 60 years of occasional studies of the Van Allen radiation belts, that there should be a new NASA mission. It's called the Radiation Belt Storm Probes, initially renamed to the Van Allen Probes mission, but it's two spacecraft in similar but nearly identical orbits. But these were to be slightly different, so one could separate them in space and tell spatial from temporal variations. And so these were put into elliptical orbits and flying through the radiation belts. Each of the instrumented spacecraft were of this configuration, had a variety of different instruments on board, electric fields, magnetic fields, and particles essentially of all energies. The one I'm going to talk about is the one that's called the Relativistic Electron Proton Telescope, or REPT. One could give similar talks to the one I'm giving about virtually all of these different aspects of these beautifully instrumented spacecraft. They operated from the launch in late August of 2012 to the time that the fuel ran out in 2019. And as the spacecraft were supposed to be commissioned over a period of several weeks, we prevailed and got our instrument turned off 2.5 days after the launch of the spacecraft. What you see here in the vertical axis at the top is basically radial distance measured in Earth radii, 1, 2, 3, 4, out to essentially the geostationary orbit. The data are displayed as a logarithmic scale in color code. The red means higher intensity. When we launched this, the activity was relatively high. There was an enhanced outer belt, and the inner belt that you can see down lower L there. And this was pretty much what we expected. But as time progressed, we saw a persistent feature. Down below, you see a projection on a meridional plane. There was a feature at about 3 Earth radii that really was puzzling. At first, we thought the instrument must be misbehaving somehow, but that couldn't have been since we built it at Colorado. But the fact was that there was a feature that was there that persisted for a month and then disappeared as suddenly as it appeared. And then the magnetosphere was struck by a coronal mass ejection, and the outer belt appeared as we expected. So what we found was that there was not, as the textbook said, 2 Van Allen belts, but often there were 3 belts. This third belt came as quite a surprise to the research community. And these results were published in Science, one of the first major discoveries of the Van Allen probe's missions. And what this really represents is a sort of a ghostly residual of previous activity that's there until a very powerful solar storm comes and wipes it out. So again, cutting this in a meridional plane projection, we see that there's the expected outer belt, the expected inner belt, and then there's this third belt that is there. There can sometimes be 4 or even 5 belts, depending on what the history is. But these are the thumbprints of previous activity, and they represent a fascinating feature. If we turn this by sort of 90 degrees, and this is the way our displays, these what we call L, or radial distance versus time kind of plots are. But you can see that over time, there can be enhancements. They can have the residual third belt sometimes. There can be a sudden loss of the particles, sudden reappearance of the particles that are usually driven by strong solar wind forcing functions, and then gradual decay away of those populations. And so the whole system is sort of like a punctuated equilibrium kind of a system. On the left side of this figure is shown the sort of anodyne conditions that may exist after there's been a long spell of quiet solar conditions, and so the belts become very weak and not much is happening. And then when there's a powerful solar forcing event on the right side, you see that there's a strong enhancement of things coming in from the magnetotail that I talked about. Wave particle interactions elevate some of those particles to extraordinarily high energies, not uncommonly to 5 or 10 megavolts of energy. And those then fill up and populate the entire outer Van Allen belt. If we look down on the top of the system, we see that the Earth's magnetosphere has, in fact, a whole zoo of different kinds of electromagnetic waves that can interact with the particles and can produce both rapid acceleration and rapid loss. And these are in different spatial regions. But as the particles drift around within these different electromagnetic wave fields, they can be scattered, they can be accelerated, they can be lost. And this mission especially working with my colleagues, John Foster from MIT and Yoshi Omura from Kyoto University. I think we've made tremendous progress in understanding how this system acts as a cosmic accelerator. So just a few thousand miles above our head is a beautiful plasma laboratory without walls that can lead to deeper understanding of cosmic significance. How do you accelerate particles from low to high energies in a very rapid and efficient manner? If we look at the long run of data, this is 6 years worth of data from the Van Allen probes. Again, this is the sort of radial distance versus time. We see that there can be periods when the intensities are very high in the outer belt. These are 2 MeV electrons. Very penetrating, can penetrate in and have the kind of space weather effects I talked about. There can be there's in this case in 2014, there was almost a year where the belts were quite devoid of activity. And then there was a long stretch in the approach to solar sunspot minimum where the intensities were very high again. And so every one of these up and down events is kind of a discrete event driven by the solar wind interactions. Just looking at one of these in March of 2013, one of the first that we studied in some detail, one can see that there was an initial enhancement. And this was just a solar wind stream that interacted, produced a lot of particles out at the outer edge of the belt system. These, you can watch them as time goes on, drifting in closer and closer to the Earth. There then occurred a very strong shock wave that wiped out the particles entirely for a couple of days. And then there was a repopulation of the belt that really led to a long-lasting and intense population across the entire outer zone. So there are really 2 main kinds of drivers. One is the high-speed streams, which tend to produce a population out further that radially diffuses. And then the coronal mass ejections that hit the magnetosphere like a hammer, accelerate the particles to quite high energies. One of the other features that is quite striking there, this is a couple of different times, but what another feature that was seen was that the high energy electrons almost never go closer to the Earth during this epoch than about 2.8 Earth radii. This was termed the impenetrable barrier. It's as if there was almost a wall, a glass wall or something that the particles ran up against, that they couldn't get any closer to the Earth than about 2.8 Earth radii. This in part could be explained by natural processes, although it's puzzling how sharply defined this was and how persistent it was. And so we began to look at other things, and we noted that there's a population of waves, electromagnetic waves around the Earth that forms what's called the VLF bubble, very low frequency bubble. A lot of this is due to waves that result from thunderstorms and other things happening within the Earth's atmosphere. But the horizontal bands that you see here, the bright red bands, are actually transmitters that are there to communicate with submarines. And these are low frequency, high intensity. And if you look at the bottom panel, you see that inside of about 3 Earth radii, the wave's intensity is 5 orders of magnitude higher inside this bubble than it is outside. And this corresponds pretty closely to where the impenetrable barrier is. And so one of the interpretations we made, again, working with John Foster, is that it may well be that in part, at least, the inner edge of the outer radiation belt is really determined by human effects. The VLF transmitters of human origin here have been communicating since the 1940s. It's quite possible that we have never seen the Earth's radiation belts in their pristine state, that they really have been we've polluted the Earth's land, its oceans, its atmosphere, and we may even have polluted the magnetosphere, the near Earth space, with our transmitters. And that would be an interesting experiment to do, but I don't suggest that we turn off the Navy transmitters. I'd rather not have a nuclear war. If we look here at look down on the top of the system again, what you see as the oval there is really the orbit of the spacecraft as they traverse across the region from near Earth out to the outer edge. They make measurements over about a 9-hour period, but the particles drift around the Earth much faster than that. So one can really take these measurements along the trajectory and really map them all the way around the Earth. And so we can get effectively a weather map of the radiation belts, much like the weather maps I suppose we see looking down at the Earth's surface. But as we map this over time, we can watch the radiation belts develop. We can see them intensify dramatically. We can see them weaken considerably, almost disappear at times. See the electromagnetic interactions occurring on all kind of time scales. And we can see the multiple belt structures sometimes. We can see the persistent nature of this inner edge, the impenetrable barrier I was talking about. And so by having these measurements continuously from beautifully instrumented spacecraft like Van Allen probes, we can really get a very dynamic picture, including the times when the belts are virtually absent. I'd like to spend just a minute to talk about not only the outer belt electrons, but also mention the inner zone protons. Using the full capabilities of this relativistic electron-proton telescope, we can essentially look at every particle that comes in, tag it, and see what its characteristics are. And by doing that, we can really get exquisite measurements of the population of high-energy protons, the ones that were originally discovered by Van Allen et al. 65 years ago, or nearly 65 years ago. Looking at these different energies, which are arrayed there from about 20 MeV up to about 70 MeV. The thing is that we see that there's an inner zone population peaking at about 1.5 Earth radii. And this has been the same, if we look back 60 years, this is almost the same as it was back in the original discovery time of the inner zone. On the other hand, there's a shoulder out there that's much higher in intensity, and this is really entrained solar energetic particles, and you can watch on daily and monthly timescales as these diffuse inward and get energized further. I would say that the inner zone population that's so persistent is really due to cosmic ray albedo neutron decay. I'd be happy to talk more if someone's interested in that. The outer part is really the trapped solar particles that are much more variable in time. And again, looking at the full capabilities of the instrument, we see that the particles extend up to, in this case, about half a GeV, and another instrument on board, Van Allen probes, made measurements up to a couple of GeV. So there's a very, very energetic particle population. Now, I will just point out that the fleet of NASA missions that are making measurements in and around the magnetosphere and of the sun is pretty extensive. But now with the loss, with the turning off of the Van Allen probes, the inner part of the system, this key part near Earth of great importance for space weather, is really doesn't have the kind of backbone of measurements that are really needed. And so working with my colleague, Tom Berger, here's in the audience, we've proposed, and we really believe that there needs to be an operational radiation belt mission. Operational means 24/7, no kidding, in perpetuity. We propose that there should be not one such pedal, but 3 pedals. We should be making measurements continuously of the radiation environment. And the more spacecraft we put in space, the more we need to understand what's happening, understand what's going on. So why, let me say scientifically, why are energetic particles so important? Well, whether we're looking at the sun or looking at the decametric radiation from Jupiter and other planets like Jupiter elsewhere, or if we're looking at, back up here for a second, or looking at the Crab Nebula, or indeed, if we're looking on the scale of extra galactic jets, all of these particles, all these systems are visible to us because of energetic particles moving in strong magnetic fields. And so we really need to use this cosmic laboratory, this efficient accelerator in our own backyard to understand how these other systems really work. So let me conclude by saying that the results from the Van Allen probes have told us a great deal about the acceleration, loss, and transport of particles. We found some fascinating new features of the boundaries and the the persistence of some boundaries that are really still quite puzzling. We know that the system behaves in this kind of punctuated equilibrium way where there are intense events driven by solar activity and then gradual changes in between these strong drivers. And we have also learned a great deal new about the inner zone and the proton interactions as well. And why have we learned so much? Well, it's really because we put new things in space, new eyes in space. And so quoting arguably America's greatest philosopher, Yogi Berra, you can observe a lot just by looking. And I would say this, that we already rue the day that we don't have this kind of backbone of perpetual and persistent, very high resolution measurements. And we really need to get that. And so we need to replace what we've had and have it as an operational system. And with that, thank you. I'd be happy to answer questions. Thanks.
Thank you, Dan, for that beautiful presentation. The graphics, the animations were terrific. Thanks.
Thank you.
Do we have any questions in the audience?
Yeah, actually, I have two. The
Okay.
first one's a quick one. Is the origin of the protons and electrons from the sun?
Yeah, effectively, these are particles that are entrained. The inner zone, I guess you could argue, could be entrained cosmic rays, but the dominant thing is really particles that have come from the sun. Yes.
Yeah. So what's the thinking? What happens during the reversal of the Earth's magnetic field?
Yeah, I would like to be around long enough to answer that question experimentally, but it's very likely that this whole belt structure has dramatically changed during those kinds of things. It might goes from probably dipolar to more quadrupolar or something like that, and probably have some very, very bizarre kind of belt structure during those times, including if the field were completely disappear, we of course would not have these kind of belts at all. And so for hundreds of thousands of years, there could be a very different spatial environment. It's a good question.
Hi, Chris Mertens from NASA Langley. I have a two-part question.
Okay.
Would the instruments that you would like to have to measure, to continue measuring the radiation belt, would they be suitable for CubeSats? Do they have the size and power to be able to do that? And secondly, if so, have people started to look at data assimilative techniques to combine this data and to produce nowcasts and forecasts of the radiation environment?
Yes, both good questions. Yes, although one couldn't do everything that the Van Allen probes did with CubeSats, there now have been a number of proposals. In fact, we've flown some instruments from our group and others and there's a new mission proposed that uses much more miniaturized kind of instruments to make those measurements. And so that's a very viable approach. And one wouldn't have to have nearly the size or mass of the spacecraft that were part of the Van Allen probes in order to do a credible job of making the measurements. And I guess with respect, your second question was about have those data been assimilated? I think it was a deficiency of the Van Allen probe's mission that there wasn't better utilization of the data, say by NOAA or the Air Force. And I think the next time we do this, we really have to make sure that these are used in a real time and a very effective data assimilative kind of a way. And that's certainly the intention. Absolutely.
Do we have any questions in the chat? Hello? Excuse me. I guess we don't. Okay. So we'll move on then to our next
Thank you.
speaker. And our next speaker is Professor Barbara Romanowitz from the University of California, Berkeley. She has a recorded presentation, but she's online to take questions afterwards. Barbara is also a recipient of the William Bowie Medal, in her case, 2019, and she's going to talk about imaging the Earth's deep interior through seismic waves. And let's see, can we?
Good morning, and thank you very much for inviting me to give this presentation in this session, and very sorry not to be able to do it in person. Earthquakes and volcanoes are the surface manifestation of the motions of tectonic plates, which themselves are driven by convective currents within the Earth's mantle, as the Earth releases the heat trapped at the time of its formation and the heat produced to this day by the decay of radioactive elements that it contains. In order to understand these important hazards, we need to investigate them not only locally, but also at the global scale, and address questions such as how the plates are coupled to the convective system below, and more fundamentally, what is the platform of this convection? Are the upwelling limbs diffuse, as we expect in a fluid heated from within? Do mantle plumes exist, as we observe in a fluid heated from below? Do the convective cells encompass the whole mantle? And also, what is the role and distribution of chemical heterogeneity in the dynamic mantle? Since we cannot directly probe below the first 12 kilometers from the Earth's surface, seismic imaging is by far the best tool we have to illuminate the Earth's interior. It does not provide information directly on temperature and composition, but rather on the elastic properties of the interior. By back projecting the time it takes for different seismic waves to travel from an earthquake to a distant station, we can infer at some level of resolution the spatial variations in seismic wave speed within the mantle. And to first order, these reflect regions where the temperature is higher. They will be manifested by slower than average seismic velocities, and regions that are colder, where the seismic velocities will be faster. There are many waves that are picked up in a teleseismic record, and classical tomography has relied on the measurements of the travel times of only a few of these seismic phases, either compressional or shear, whose path through the mantle is well understood. One of the main challenges of global seismic imaging is that we rely on natural earthquake sources, which are not distributed uniformly around the globe, but mostly follow the plate boundaries. Also, most recording stations are on land, leading to a much poorer illumination of certain areas of the deep interior, in particular in the southern hemisphere and, of course, in the oceans. Nevertheless, progress in deep Earth imaging in the last 40 years has benefited from the development of highly sensitive digital, broadband, and very broadband seismometers, which happened in the 1970s, and the huge international effort that has followed in the deployment and the collection of the corresponding data sets in largely open access data archives, led, for example, by the IRIS one in the US and the Orpheus one in Europe. The first global tomographic models were constructed in the late 1970s, but the first detailed images of subducting slab, which lend themselves well to P and S travel time tomography because of good illumination from many directions, these were obtained 20 years later. As you can see from these depth cross sections across the entire mantle, the location of the cuts are indicated in the plot below. The colder than average subducting slabs can be followed into the mantle and exhibit different behaviors, some of them spreading in the upper mantle transition zone, but some of them extending deep into the lower mantle. This was a revelation for geochemists, showing evidence for material transfer between the upper and the lower mantle. More recently, it has become clear that in some regions, here in Fiji Tonga, slabs actually spread or pond deeper, around 1,000 kilometers depth, while spreading in the transition zone could be understood because of the slowing down effect of the 660 kilometer discontinuity, which is a phase change with a negative Clapeyron slope in the olivine system. No global phase transition has been documented by mineral physicists at 1,000 kilometers, And understanding this remains one of the hot topics of today's research. Slabs that were once subducting near the surface may now be residing deep in the mantle. If ancient slabs can be identified in tomographic images, as is attempted in this study, this can provide constraints on the evolution in time of subduction and therefore on plate organization back in time. Today, higher resolution P-travel time tomography is used in conjunction with paleomagnetic and geologic data to produce detailed tectonic reconstructions going back to at least 250 million years, with the added advantage that if one accepts these interpretations, seismology provides constraints on the paleolongitude of the continental masses involved. Teleseismic P and S waves dive deep into the mantle and provide poor coverage of the oceanic upper mantle. For this, surface waves, which travel along the surface of the Earth with diminishing sensitivity with depth, offer the opportunity to develop global long wavelength models of shear velocity structure in the mantle. This model, one of the first built using global surface wave data, and here shown in a map view at a depth of 100 kilometers, already shows the main features expected from plate tectonic theory very clearly. The ridge system, where hot material is rising to form new crust, is manifested by lower than average shear velocities, the red colors here. The old cratonic cold centers of the continents are blue here, regions of faster than average velocity. And we can even see the cooling of the Pacific plate as it ages, as you can compare here with a map showing the ages of the oceans. This is a wonderful confirmation that mantle tomography works. The resolution has improved over the following 25 years, but the main first-order features remain the same. Surface wave travel time measurements also give access to imaging seismic anisotropy in the upper mantle. Here, the so-called azimuthal anisotropy, which expresses at the large scales the alignment of anisotropic olivine crystals with the flow. The red bars indicate the directions in which the seismic waves travel the fastest. This can be related either to fossil plate motion directions at lithospheric depths, as here seen in the Western Pacific Ocean, or to the present-day plate motions at astenospheric depths, as shown in this plate. Combining the travel time information from surface waves, their overtones sensitive to deeper depths, as well as travel times of body waves sensitive to shear velocity, one can build global whole mantle long wavelength shear velocity models. Several different groups developed such whole mantle long wavelength model with good agreement on the main features as we go down from the uppermost mantle to the core mantle boundary. I'm showing just one of these here in map view at different depths from the top to the bottom of the mantle. A remarkable observation is that the spectrum of heterogeneity is dominated by very long wavelengths, the so-called degree 2 in spherical harmonics expansion, at the top and at the bottom of the mantle, as would be expected if those are the boundary layers in a convective system spanning the whole mantle. The top map at 100 kilometers is the same as I previously described and shows the correspondence of the structure with the surface tectonic, which persists down to about 200 kilometers depth. As we go deeper, that connection is progressively lost. Instead, we see the signature of slabs ponding in the transition zone, as seen in these depth cross sections from a higher resolution P-wave model. The white bars indicate their location. And then deeper, we see other slabs ponding at around 1,000 kilometers depth. In the deepest mantle, the structure changes significantly with a ring of fast velocities surrounding two quasi-antipodal regions of low velocities, which have been named the LLSVPs, which stands for Large Low Shear Velocity Provinces. While the ring of fast velocities can be related to the graveyard of slabs in the last 300 million years, the LLSVPs are fascinating structures whose nature and role in the global circulation are not yet well understood. The highly organized structure of the LLSVPs is robust across models developed by different groups in the last 20 years, as shown here for 3 of them. If one extracts its longest wavelength component, the so-called degree 2, here in 3D rendering, the antipodal equatorial position of this component of the LLSVPs is striking, as is the fact that the ring of fast velocities contains the location of the present-day pole of rotation of the Earth, as well as the paleopole locations going back 250 million years at least, which suggests a stable configuration from the point of view of the moments of inertia of the Earth. This structure is also reminiscent of one of the simplest forms of convection in a sphere, with two antipodal upwellings and one ring of downwelling between them. Another piece of evidence for the stability through geological time of the LLSVPs, at least recent geological times going back 300 million years, is the correlation of the position of large igneous provinces with the borders of the African LLSVP. The potential stability of the LLSVPs through time suggests that they may be heavier than their surroundings and therefore of distinct composition. In fact, there are several other observations that I'm going not to show all of them that support this view. Forward modeling of seismic waves, for example, that interact with the borders of the LLSVPs show that these boundaries are sharp. There is also evidence for anti-correlation of shear and bulk sound velocity, documented first from P and S body wave travel time tomography, but it's also seen in the change of the ratio between S and P heterogeneity with depth in the long wavelength models. This ratio attains values in the lowermost mantle that cannot be explained by lateral variations in temperature alone. Some normal mode-based studies have suggested that LLSVPs, at least in the longest wavelength expression, are denser than their surroundings, which would make sense if they are stable features over hundreds of millions of years. This has inspired dynamic modeling of LLSVPs as dense, tall piles swept around by the background circulation, and specifically by slabs arriving at the base of the mantle. But this is still a topic of debate. Although a new technique based on the analysis of solid Earth tides has embraced this interpretation, other normal mode studies are finding the opposite, namely that the LLSVPs are lighter than their surroundings. So this remains an open question, a challenging one, since most imaging techniques are not directly sensitive to density, while normal modes, which are sensitive to density variations, have limited spatial resolution. So the debate is open, as well expressed in this cartoon by Ed Garnero. Are the LLSVPs dense, stable, or metastable piles extending high above the core mantle boundary? Or are they perhaps simply a bundle of mantle plumes restricted between regions of subduction, which simply cannot be well resolved by long wavelength seismic tomography? This brings me to the topic of mantle plumes. At the time of the plate tectonic revolution in the 1960s, Tuzo Wilson and Jason Morgan proposed that mid-plate hotspot volcanism may be due to the presence of plumes of hot material anchored somewhere in the deep mantle and fixed with respect to the motion of the plates. There is indeed a lot of evidence from radiogenic trace element composition of hotspot lavas that hotspot volcanism may be tapping a distinct ancient reservoir preserved deep in the mantle. Also, thermal convection models in a fluid heated from below show the formation of plumes with narrow stems and broad heads. Scaled to parameters relevant to the Earth's mantle, these plume stems would be no more than 200 kilometers wide, so that resolving them presents a challenge for seismic imaging. One challenge is that most hotspots are located in the middle of ocean basins where the illumination by travel time tomography is the poorest. As seen in this checkerboard resolution test of P-wave travel time tomography, a checkerboard with very large cells is barely resolved in the oceans. Another challenge is that low velocity bodies of small lateral extent, such as could be expected for classical mantle plumes, may be hidden from view, or at least poorly resolved by travel time tomography, which relies on measuring the first onset of P or S waves. The first arriving waves actually do not sample the low velocity anomaly. They go around it, so that one needs to dig deeper into the waveform to take advantage of the broadband or finite frequency character of the waves. Theoretical progress made it possible to take advantage of the finite frequency character of recorded seismic waves and take into account the sensitivity to a broader region around the infinitesimal rate path. And this led to some spectacular images, which are now almost 20 years old, that revealed the possible presence of low-velocity conduits between many hotspot volcanoes down to great depths. Skeptics, however, put into question the actual continuity of these structures with depths, and that these features might be due to possible smearing effects when using only direct P and S waves, as most of the corresponding volcanic islands are isolated in the middle of the ocean and therefore not well illuminated by crossing wave paths from different directions, which is an important condition for tomographic resolution. Clearly, there is more information in a seismic record than provided by the direct waves alone. So the obvious way to compensate for the poor distribution of sources and receivers around the globe is to take advantage of all the later arriving waves that are bouncing around the mantle, providing many opportunities for improved illumination of deep and smaller scale mantle structure. This has led to the development of full waveform tomography, which requires the computation of the seismic wave field in a complex 3D model to be compared to the observed seismogram, and rather than just the travel times of a discrete set of seismic phases well separated in the seismogram. Although already developed many decades ago, for a long time this approach suffered from the fact that the synthetics could only be computed approximately, therefore limiting the resolution that could be attained in the structure. A real revolution in global seismic tomography came with the introduction of the spectral element method, a numerical method of integration of the wave equation, which allows accurate computation of the wave field practically regardless of the scale and size of heterogeneity in the model considered. And this gives access to improvements in models that lead to higher resolution, in particular of small-scale, low-velocity structure. This, of course, comes with some drawbacks, the most important of which is the computational time, which increases as the fourth power of frequency and requires access to HPC computing facilities and many hours of computing time, in particular because this is a nonlinear inverse problem, which requires many iterations. Nevertheless, the imaging methodology that relies on these computations has revealed some intriguing structures in the last decade, and I will spend the rest of my time discussing those as they open up many new avenues for further research. I'll be showing a series of depth cross-sections from the top of the upper mantle to the core mantle boundary. The geographical position of these cross-sections is indicated on inset maps beside each of the cross-sections. We now have a much clearer evidence for the presence of broad columns of low shear velocity material extending vertically from the core mantle boundary to the upper mantle in the vicinity of the location of major hotspots, as shown here beneath the Pacific. These broad plumes appear much wider than expected for purely thermal plumes. Also, besides the resolved fat plumes, there are others much thinner, barely resolved here, and which are better resolved in regionally focused studies, such as here beneath Yellowstone. Such fat quasi-vertical plumes in the lower mantle are also seen in the Atlantic hemisphere. While still not very detailed, their first-order features are confirmed in more regional studies, such as here beneath Iceland. Notice in particular the horizontally oriented portion of the low-velocity region in continuation of the deep mantle plume around 1,000 kilometers depth. So these image plumes are thicker than expected for purely thermal plumes. This can be confirmed by resolution tests, which indicates that they are either thermochemical plumes that entrain dense material from their base, possibly ancient oceanic crust brought to the core mantle boundary by subduction, or they may be the manifestation of nonlinear rheology in the lower mantle that also would tend to modify the shape of the plume and broaden the width of its thermal signature, as seen in these experimental results. Such nonlinear rheology is challenging to implement in whole mantle numerical convection models. As I already mentioned, an intriguing feature of these fat plumes is the deflection and spreading of the low-velocity material at the base of the extended transition zone, around 1,000 kilometers depth, where, as it happens, we also see horizontal spreading or deflection of some slabs. and which suggests the presence of a possible rheological boundary at that depth. There is no agreed upon mineral phase transition at this depth yet. However, a discontinuity around that depth has been picked up sporadically in some seismic studies of scattered waves. Explaining this remains a topic of active research. In the current global whole waveform inversion models, here's a more recent one by the Princeton group, the fat plumes often seem to disappear at shallower depths, which in fact is likely due to a loss of resolution, as we expect them to be thinner in the upper mantle where the viscosity is lower. Note that the two FWI global models shown here were developed using rather different approaches and datasets, but agree on the first order features of this and many other plumes. A recent higher resolution regional study from my group, focused on the mantle beneath the Atlantic, appears to detect the continuation of some plumes, here Cape Verde, into the upper mantle, where they are thinner and meander up to the corresponding hotspots, perhaps following paths such as the one indicated by the white arrow here. An interesting observation is that the fat plumes are detected only under those hotspots that lie above the LLSVPs. The map shown here is just above the core mantle boundary at 2,800 kilometers depth, and not those that fall over the ring of fast velocities surrounding the LLSVPs, such as, for example, Yellowstone and other hotspots indicated here by the green dots. This brings up the question again as to whether the LLSVPs are compact structures or perhaps formed each of a bundle of plumes that have developed away from the ring of downwellings. The two available FWI global mantle shear velocity models seem to disagree on this point, at least in some areas, such as here beneath South Africa, where CNUCB shows 3 separate plumes, but the Princeton model shows more like a compact pile. Our most recent Atlantic-focused model seems to confirm that there are indeed separate plumes, at least one of which reaches all the way up to the extended transition zone. I need to step aside for a moment to define the concept of ultra-low velocity zone. These patches of very strongly reduced compressional and shear wave velocity extend only a few tens of kilometers above the core mantle boundary. They were discovered by forward modeling of seismic waves that spend some time at the core mantle boundary, propagating along the core mantle boundary as P waves. They have been found in many locations since then, mostly within the borders of the LLSVPs, and in general, they span a few hundred of kilometers laterally. They are not yet accessible to tomographic imaging because of their small height and the high frequencies necessary to image them. It turns out that a mega version of an ultra-low velocity zone was detected at the root of the Hawaiian plume from forward modeling of 10 to 20 seconds S-diffracted waves that propagate along the CMB and which show waveform complexity that is not predicted by any tomographic model, but that can be well explained by a lensing effect with associated diffraction pattern from a very anomalous, large 800 kilometers wide lens. Such mega ULVZs have now been found beneath several other hotspots associated with fat lower mantle plumes, raising the question of whether this is a systematic feature within the roots of all fat plumes, which might point to the presence of partially molten, denser material that could stabilize the plumes and also could help reconcile different views of the density structure of the LLSVPs at long wavelengths, as the dense material could be localized in thin, discrete patches extending only a few tens of kilometers above the core mantle boundary. The current global tomographic images produced by FWI, which are slowly coming into better focus, inspire new questions about the dynamics within our planet's mantle. Evidence for much slower, sluggish circulation in the lower mantle, more vigorous mesoscale convection in the upper 1,000 kilometers that I have hardly discussed because of lack of time, but for which there is also mounting evidence, and which could explain deflected slabs around 1,000 kilometers depth and entrainment of thinner plumes towards hotspots. The list of questions going forward include LLSVPs, giant compact piles extending high into the lower mantle or bundles of thermochemical plumes. What is happening at 1,000 kilometers depth? is at a boundary for mantle dynamics, but there is no known change of deformation properties known at present. Do all major plumes contain ultra-low velocity zones at the roots? Is there a layer of primordial material at the core mantle boundary that feeds these plumes, giving rise to the different composition of basaltic lavas in hotspot volcanoes? And I have not discussed this, but these are questions that are coming up. Can this distinct signature come from the core rather than from the mantle? Before I finish, I'd like to briefly mention the way ahead. Clearly, we need better coverage of the oceans. The current MERMAID program, which sends floating hydrophones that detect P waves from earthquakes, sampling different regions of the oceans as they are moved around by currents, show promise for covering the oceans with P waves and possibly converted S to P wave observations. However, there is still room for installing broadband stations on the ocean floor. 20 years ago, we reasoned in terms of permanent observatories, but that never really took off due to excessive costs and the logistics of providing power and retrieving data over long time periods. But the new concept of ocean bottom broadband deployments in the form of arrays over periods of several years is attractive, especially if such arrays can attain larger aperture. Also, the new DAS, distributed acoustic sensing technology, which is still in its infancy, holds promise for utilizing fiber optic cables in future dense recording of seismic waves across the oceans. And finally, there is still room for theoretical methodological improvements that can speed up the inversion process. Many of those are presented at this AGU meeting. I will just mention one example that we are pursuing in my group. The box tomography methodology allows us to compute the full teleseismic wave field, sampling a deep target region of the mantle only once and iterating the inversion in a much smaller domain, reducing the computational burden significantly and possibly making it one day feasible to apply Bayesian modeling and AI to the global mantle tomography problem. With this, I thank you for your attention, and I'm happy to take questions if there is still time.
Thank you, Barbara. Do we have any questions from the floor? So is there one back in the room there, in the back of the room? No. Okay. Barbara, I have a question for you. Actually, I had two questions for you, and you answered the first one with your last few slides, which was what sort of emerging technologies are there to improve sampling in the oceanic domain? And you answered that very well, thank you. But my second part of that question is, what are the most important advances you think those new measurements will provide in terms of our understanding of the Earth's interior structure and its geodynamics?
Well, if we can improve the resolution of structures through imaging, we can start to look in more detail at how the how the tectonic plates are coupled to the underlying circulation in many different ways. We can answer questions about the geochemistry of hotspot volcanoes. Where is that coming from? Where basically understand many of the observables from other disciplines than seismology, higher resolution.
Okay, thank you. Other questions? Do we have any from the chat? Any questions from the chat? Let's see. No questions from chat? Okay, thank you. All right, Barbara, thank you very much for that excellent presentation. We'll move on to our third and final speaker, who is Professor Tong Zhu from Peking University, who is one of the most highly cited Chinese researchers in environmental science. And the topic of his presentation is the health effect of air pollution. And his presentation is also recorded and not be online to answer questions, but you can contact him through the AGU meeting app if you have any questions following his presentation.
Good morning, afternoon, and evening, everyone. First of all, I would like to thank the conveners of this session for inviting me to give a talk about health effect of air pollution, fine particles. I'm Tong Cu from Peking University, Beijing, China. When we look back 100 years in the past, air pollution was and is still a global challenge of environment. The pictures showing from either from London, Los Angeles, Mexico City, and Beijing, Delhi, and even Paris, all the air pollution has caused a serious environmental problem and also cost the lives of the people living there. Take London, for example. The London smoke, very famous one, was happening in December 1952. While the city was barely visible during the day and the night, and we can see with the increasing the level of smoke and the deaths per day has also following this trend. Before the smoke, the deaths per day is about 250 or 60, but it's increasing quickly into about 800 per day. So this extra days is the evidence that air pollution can actually cost human lives. Our knowledge about the health effect of air pollution has been gradually improved through the epidemiological study. One of the most important and famous one was the 6-city study by Harvard University, which carried out the air pollutant monitoring over 6 cities in eastern part of US. It started with total particle measurement in 1970s and added to the fine particle measurement in 1980s. And in the meantime, it followed the health condition of about 9,000 subjects. Throughout the 15 years cohort study, the number of deaths of each city has been recorded. And if we plot the probability of survival of different city, we can see in the 15 years, there's a decreasing trend and different city have a different rate of decreasing. And if we plot the fine particle concentration of these 6 cities, and if we compare those cities with of the relative risk of the mortality, and we can see the city Portage with the lowest PM2.5 or fine particle concentration as the comparison, and the other city has gradually increasing of the rate ratio or relative risk. This is almost linear exposure response relationship. The Harvard 6-city study published in the New England Journal of Medicine in 1993, together with other studies published in the same time, were taken by US EPA as evidence and to introduce a national ambient air quality standard for PM2.5 in 1997. And this proposal encountered a strong challenge by industry and the lawmakers. There's a strong debate where the study itself were robust enough. So there's argument would like to re-auditing the data from the Harvard 6 studies. And then there's also an argument to require to have repeat measurement or repeated study. Evidence from a cohort study of American Cancer Society, which cover about 500,000 subjects, provide a strong support to the Harvard 6 city studies. It also shows clearly those exposure response relationship with the increase of the PM2.5 concentration. The all-cause mortality relative risk is also increasing, and especially those with cardiopulmonary disease and lung cancer increase even higher. So this is adding to the evidence that the PM2.5 is robustly associated with mortality. In the year 2005, World Health Organization released its first Global Air Quality Guideline, or AQG. And in this first Air Quality Guideline global, it is for the first time included PM2.5 into it. And it also set on its entry targets for the different country to refer to. So we can see that for the PM2.5, the annual mean concentration should be 10 microgram per cubic meter, which is very impossible for many developing countries to meet. So it says that inter targets 1, 2, 3 at a different level of 35, 25, 15 for the countries to refer to settle their ambient air quality standard. Since then, many countries adopt the air quality guideline from WHO to its national ambient air quality standard for PM2.5, which you can see for China, we used Intertarget 1, which is 35 microgram per cubic meter. And there's many other European countries using Intertarget 2, 25 microgram per cubic meter annual mean concentration. And there's other countries like US, Japan, using even much lower concentration, which is 15 microgram per cubic meter for PM2.5. So what is PM2.5 or fine particles? PM2.5 is an aberration of particulate matter with aerodynamic diameter smaller than 2.5 micrometer. We use cyclone to take air with particle into our sampling system, and the speed of air into the cyclone will define the aerodynamic diameter of particle we were taking. So that's how we call it aerodynamic diameter. In the air, there are particles from nanometer to 100 micrometers. And the study suggests those particles with smaller size, like PM10 or PM2.5, has the most serious health effect because they can inhale into deep into our lung. And so this is how the PM2.5 compared to our hair looks like. This, if we use this blue sphere as PM10, and there's 2.5. And here is how the routine sampling of PM2.5 filter, the inlet will define the particle size, and the filter inside will collect the PM2.5 particle. So PM2.5 is a mixture of particles with all the size smaller than 2.5 micrometers and with a very different chemical composition because it has a very complicated source. Could come from the combustion, diesel exhaust, also chemical reactions leading to the secondary aerosol particle component like sulfate, nitrate, ammonium. And there's also elemental carbon, heavy metals, and clays mixed with that. So it has a very complicated source, chemical compositions, and size distribution. In order to understand the complex sources and the chemical reactions leading to the formation of PM2.5, advanced instruments have been developed to measure chemical compositions and the size distribution of PM2.5, like the particle sizer or ambient continuous multimeter monitoring, using the energy dispersive X-ray fluorescence analysis, or online monitor for aerosol and gases in ambient air, which can measure water-soluble ions in PM2.5. Sophisticated online instruments have also been developed, like this non-time of flight high-resolution aerosol mass spectrometer by Aerodan. Sophisticated instruments have also been developed to measure single particle of PM in the air, like the atomic mass aerosol time of flight mass spectrometer by TSI, and also single particle aerosol mass spectrometer by Hexin. When the aerosol particle was introduced in the system, 2 laser beams mirror its size and another laser to ionize the particle, and the vaporized ions then will be analyzed with time of flight mass spectrometer. In the meantime, local, national, and global monitoring network of PM2.5 has been established. Take China, for example. Its national ambient air quality monitoring stations for PM2.5 has expanded from almost none to more than 2,000 in the last 10 years. And in the WMO, the Global Atmosphere Watch Network, it also includes PM2.5 into its monitoring parameters. Different research platforms such as aircraft, airship, smoke chambers, and the satellite have been developed to understand the chemical process in the atmosphere. And this comes together with intensive field campaign in different countries, was hoping to understand the source, transport, and the transformation process of PM2.5 formation. Sophisticated regional and global models have been developed to simulate and forecast PM2.5 concentration at a local, regional, and global level. For example, the weather research and the forecasting model coupled with chemistry, WolfChem, provides different scale of PM2.5 concentration in the different region. Using the satellite-based aerosol optical depths, such as Moody's and MISA, combined with the global scale atmospheric chemical model like GeoScan, we can retrieve PM2.5 concentration on the surface. The satellite retrieved PM2.5 concentration globally is very important for the countries with no PM2.5 monitoring station. Combined with the exposure response relationship established with epidemiologic study, one can estimate the global mortality from the PM2.5 exposure. So that in the early stage, the Global Burden Disease Report in 2010, it found among all the risk factors for mortality, like dietary risk, high blood pressure, tobacco smoking, ambient particulate matter pollution, which is mostly PM2.5, leading to about 3.2 million deaths globally. And it is ranked the 7th in the risk factors for mortality. Since the publication of the Harvard six-city study, extensive epidemiological and toxicological study have been carried out. Now we have been not only have extensive evidence for the association of PM2.5 with the health effect, but also evidence for the biochemical mechanisms on the effect of health of PM2.5. Now we understand once inhaled into our respiratory system, PM could cause our autonomous imbalance. It also leading to the systematic inflammation and also be transmitted into blood, leading to the damage of our cardiovascular system. So once particle into our lung system, leading to the oxidative stress, inflammation, and the ion channel activation, then it will lead into the produce of biological intermediates causing autonomic imbalance and HPAX activation. And eventually it will lead into the epigenomic changes, tissue inflammation, thrombosis, plaque instability, endothelial damage, vascular dysfunction. China has experienced very fast economical and social development in the last decades. In the meantime, it also suffered severe air pollution in the last 2 decades. The severe air pollution almost 10 years ago has helped the Chinese government make up their determination to control the air pollution. So they first in 2012 introduced PM2.5 into its national ambient air quality standard, following WHO air quality guideline entry target 1, which is equivalent to 35 microgram per cubic meter annual mean concentration. And once it has the national ambient air quality standard, then it is able to start a national action plan on air pollution prevention and control. This 5 years plan has set its target to reduce the PM2.5 concentration nationwide, and basically many cities like Beijing and regions like the Yangtze River Delta. So in order to enforce this prevention and control action plan, Chinese has set up its policy framework for air pollution and prevention control. It has 3 parts. First, capacity building to monitor, forecast, and report air quality, most importantly, PM2.5 concentration. And to understand the emission source of the PM2.5, and all these measures is targeting on the industry and the different sector for the tailpipe controlling and also energy structure shifting. And finally, it has also legislative and economic measures, and as well as administrative measures to ensure the action plan works. Under this action plan, China has established PM2.5 monitoring station from almost none to 500 to more than 1,500 to more than 2,000. With the National Action Plan for Air Pollution Prevention and Control, PM2.5 concentration has been drastically reduced from 2013 to 2017, about 33% reduction, both from the observation and from the simulation. The continuous effort to reduce air pollution from 2017 has helped PM2.5 levels to further reduce to under the national ambient air quality standard. So for the first time in 2021, Beijing's air quality met national ambient air quality standard. One important aspect is that the health benefit from PM2.5 concentration reduction is tremendous. From 2013 to 2017, with the reduction of PM2.5 concentration nationwide in China, and in total, we see the mortality has been reduced by more than 200,000. This is a huge number in the sense of the health burden caused by exposure to PM2.5. The drastic reduction of air pollution, especially PM2.5 levels in the cities in China, is a significant progress. However, there's no time for us to celebrate because in 2021, WHO have updated its air quality guideline, and especially for the PM2.5 annual mean concentration, it has reduced from its original 10 microgram to 5 microgram per cubic meter. The new air quality guideline is based on extensive new evidence of epidemiological studies, like it's based on 41 different cohort studies around the world to establish the association between long-term PM2.5 exposure and the mortalities. And it's also based on the data from 652 cities worldwide to estimate the daily average of PM2.5 concentration with daily all-cause mortality, leading to the guideline for the daily mean concentration. The reason that new air quality guideline has reduced annual mean concentration for PM2.5 from 10 to 5 microgram per cubic meter is based on 18 studies. And among these 18 studies, 5 studies found the lowest PM2.5 concentration at this level will be able still to see the health effect is around 4 to 43 microgram per cubic meter. It is very important to note that the new air quality guideline could protect more lives. If we use 2020 as a baseline, if China meets 35 microgram per cubic meter, which is the national ambient air quality standard for PM2.5, then we could avoid 116,000 deaths per year. However, if we reduce air pollution to 10 microgram per cubic meter, then we could avoid almost 1 million deaths per year. Even if we're working harder to meet the new air quality guideline of WHO, then we could avoid extra 285,000 deaths per year in China. However, the complex nature of the health effect PM2.5 make its control much more difficult and challenging. We know if we compile all the information about the health effect of PM2.5, we can use 4 dimensions to describe. First, the time after exposure and the different disease will happen after exposure. It could be a few days, a few months, or a few years. And the different size of particle, even the smaller finite parts of PM2.5 can deposit at a different fraction into our lung system. So if there's even finer particle, like the ultrafine particle, which is size smaller than 100 nanometer, should be also cause even larger effect, which is more evidence. Now we know PM2.5 is a complex mixture of all the chemical components, including the inorganic transition matter, for example, and the organic like pH and the quinone-like matters. So they should be taken into consideration. And finally, different people could be vulnerable to the exposure of PM2.5, like those children, elderly, female, and people with disease, and they could be caused by the even larger health burden by the exposure to PM2.5. Increasing number of studies also indicating that people with disease at young and elderly are most vulnerable to PM2.5 exposure. It is estimated about 40% of COPD deaths, 26% of stroke deaths, 20% of asthmatic heart disease, 90% of lung cancer, and 30% of non-respiratory infection deaths, 20% neonatal deaths, and 20% of diabetic deaths are attributable caused by PM2.5. The updated WHO air quality guideline and the new evidence that air pollution causes the health burden not only in the common population, but to the vulnerable population, indicating the urgency to reduce the PM2.5 exposure. So this is a big challenge for the countries, especially Environmental Protection Agency, to take action. The good news is the carbon neutrality policy committed by different countries provide excellent opportunity to reduce PM2.5 concentration. For example, this study found if China meets its carbon neutrality goals by 2060, then 78% of Chinese population will be living in the level of PM2.5 lower than 10 microgram per cubic meter. And now there's a lot of discussion. How can we combine the air pollution control policy with climate change mitigation and adaptation policy? And now we have the National Ambient Air Quality Standard. We should be able to update it. And how can we use the carbon neutrality to reduce the air pollution at the same time to improve our health? So the question, if we could maximize co-health benefit of air pollution and climate change, and how? In the 1990s, robust PM2.5 association with health effects have been established, and the scientific research have made tremendous progress in understanding the sources and the formation process of PM2.5 and to forecast it. WHO included PM2.5 in its global air quality guideline, and its global burden of disease estimates PM2.5 caused more than 4 million deaths globally each year. These actions help countries to set national ambient air quality standard for PM2.5. US, European countries, and China have significantly reduced PM2.5 concentration and saved millions of lives. In the future, carbon neutrality provides a unique opportunity to reduce PM2.5 to a much lower concentration. How to coordinate air pollution control and climate change policy to maximize the co-health benefit is a question to be answered in the coming years. Thank you for your attention.
Well, Professor Zhu is not online, so we won't have the opportunity to ask him questions. But again, if you have any, you can reach him through the app. This concludes our union session. Thank you all for attending, and thanks once again to the speakers, all of whom gave really excellent presentations. So enjoy the rest of the meeting. And Friday session on imaging the Earth's surface is the second in this series of AGU College of Fellows Legacy Committee convened sessions. You might want to check that out. Thank you.